Okay.
Good evening, sir. Good evening, sir.
Sir,
I'm
I
the
just wanted to ensure whether it is clear from our end.
Hello.
Yes, sir.
So you can hear me, right?
Yes, sir.
Okay,
So,
okay, great. Yeah.
so I'm the anchor for today's program. So,
Mm,
may I start? Yes, sir. So, the future of artificial intelligence depends on mathematics. As AI systems become more complex, they will require more sophisticated mathematical models. The mathematicians of tomorrow will be the ones who build the AI systems of tomorrow. Good evening to one and all present here. I, Adasha Patnaik, the anchor of today's event, would like to extend a warm welcome to you all wholeheartedly to the International Workshop on Recent Trends in Computing and Mathematics 2023. So, this is a 5 days program which started from the 18th of August 2023, will continue till the 22nd of August 2023, and now we are successfully conducting a 4 day seminar. This is simply a golden opportunity to get to learn a bountiful of information and knowledge from our esteemed guests. This is not just a workshop, but also an amazing interactive session where the students get to rack through their brains and ask away their queries and have loads of fun while learning. We are highly honored to have such a distinguished group of guests here today, including professors, researchers, young students, and our college dignitaries present here with us virtually in the meeting today. We are highly privileged to have with us our guest of honor with us today. And now I would like to introduce our esteemed guest faculties.
uh, Hello.
Good evening, sir.
Yeah. So I can start now, right?
Sir,
So,
I'd like to some add up to that a bit.
okay.
So may I? So with this, we are going to begin session one of today's program. Ladies and gentlemen, esteemed colleagues and honored guests, it is with great pleasure that I introduce to you a prominent scholar and esteemed educator, Professor Ben Han. Professor Ben Han is working in Department of Mathematical and Statistical Sciences, University of Alberta, Canada. He has published 112 referred SCI journal papers and one 724-page research book. Ranked number 1688 worldwide and number 68 in Canada for top scientists in mathematics. Editor of 4 academic SCI journals, presented 8 plenary talks in international conferences and numerous invited talks. Supervised 4 postdoctoral fellows, 7 PhD students, 5 MSc students, and 10 undergraduates. His research interests include computational mathematics, scientific computing, and data science. His talk is based on 4 wavelet and Sobler spaces and their applications to numerical PDEs. We extend our heartfelt gratitude to Professor Ben Han for gracing our event with their esteemed presence. Your insights have enriched our gathering and inspired us all. Please, sir.
Yeah. First, I'd like to thank you. Nice introduction. So I'm very glad to talk to you about some of my recent research. So the topic of today's my talk is on using the Williams method in the subnet spaces and with the applications to numerical PDs. So let me start. The full screen. Okay. So the first topic I'm going to talk about is so which kind of wavelengths we are going to use to solve PDEs. So this is a sharp contrast to the wavelength applications to image processing. So if we are only interested in the image processing, we are deal with bi-orthogonal wavelengths in L2. But in order to solve the problems for numerical PDE, in particular for the boundary value problem, then we have to use bi-orthogonal wavelengths in the subnet spaces. So let me start with this. So what is risk waveness in the Sobolev spaces, HMR? So the definition of the Sobolev spaces for Hm to the power m on the real line. So m, generally speaking, is in positive integers. For example, if m equals 0 here, so the Sobolev space with m equals 0, this is just the L2 space. But if m is positive in integers here, so by what we mean f belongs to Hm, we mean the weak derivatives of f, so f prime, and go all the way to the power m. So this is the derivative, m's order derivative in the sense of in the weak sense. So if all the functions f to the derivative of m belongs to L2, then this function is said to be belongs to the Sobolev space Hm. And its Sobolev norm is defined as L2 norm all the way to the derivative to the order m. And this just put them together. And then generally, because we square them, then we need to take a square root. This gives you the Sobolev spaces. So if we are interested in using waveness to solve numerical PDEs, then you are going to see the most popular Sobolev spaces generally is H1 and H2. So our main goal in this talk is that we are going to deal with the Sobolev space H1. So now the next is how we are going to talk about the risk waveness in the Sobolev space is deal with so basically you deal with not only deal with the scalar waveness here. Why the sign is always sneakery is a little weird. So maybe just using this I can write. Just wait a second. Okay. So basically what we are talking about is so when we talk about the multi-waveness here, so this means this function is no longer one single function. It's generally the vector of functions here with R component. And from this refinement function, then we're going to derive the waveness here. So the waveness generally is also from psi 1 to psi s. In the most of the case, s equals r. So this is the multi-waveness. And the function space we are interested in the Sobolev space Hm. So by what we mean, this pair, the phi and psi, is a risk wavelet in the Sobolev space Hm. This refers to a big system generated by the phi, basically by this vector phi, and also another vector psi here. They are going to generate a huge system. So this huge system has two parts. So the first part is an integer shift of this function. So k is an integer. Then you translate this function by integer k. And for the psi part, so basically this is a wavelet part. Then we are going to have this dilated and shifted function. So this phi jk generally is defined in the standard way. So basically you are going to deny the function by 2 to the j. So basically you are going to stretch them. So you stretch this x by 2 to the power j times x, and then you also shift them by k. So this definition of psi jk generally is corresponding to this space, the one you are going to read in a lot of textbook. But if we are interested in the Sobolev space Hm, then you are going to see the very interesting normalization here. And so after we using the dilates, which is j, and also translation k, then we are going to have a huge system here. So before I move on to give the definition, let me explain to you. So why we have this strange factors here. So this factor 2 to the power negative mj, basically you are going to see, if we are going to define function this way, so it's very easy to check that this function L2 norm, you can do a very simple calculation. So you are going to see in the sense of L2, so this factor 2 to the j divided by 2, and will make this L2 norm of this function equals the norm, L2 norm of this side. So basically they have the same L2 norm. So what is this strange scaling factor? Basically it's because we're dealing with Sobolev spaces, and what we want is we want this 2 to the minus mj, and we also have a psi jk. So how you are going to measure them? You are going to measure the norm in the HM space. And if I'm going to measure this one in the Sobolev space HM, then you are going to see this is more or less is no longer equal sign. So and this also in the so this norm is this L2 norm. So you are going to see, if you want the HM norm, this one of this function to be more or less like a constant, so means independent of j and k, then you need to add this factor 2 to the minus m and j, and this is fairly important. So after we have this one, then by what we mean Reitz wavelength in the HM, basically just means this collection of elements in the Sobolev space HM, they satisfy this two conditions. The first one is a stability condition. So if you are going to use this linear combination of elements from this, so basically for any elements in the ASM, then you make a linear combination by taking coefficients HM, and you measure this one, the HM norm, and you are going to see the HM norm should be more or less comparable to the neutral L2 norm. So with the upper bound and the lower bound. So this just means this system ASM, phi and psi, this is a Reitz sequence in the Sobolev space. So basically means you have a upper bound and a lower bound, and the HM norm is equivalent to the neutral L2 norm. And for sure, you want the linear span of the elements in this one is also dense in HM. So this is the definition of the Reitz wavelengths in the Sobolev spaces. And the most popular case is corresponding to this neutral m equals 0. So in this case, the Sobolev space H0 is nothing else here. So h to the power 0 for the Sobolev space is exactly just means the square integrable function space L2. And so by what we mean, once again, by what we mean the multi-wavelengths here, this refers to this one. So this is a vector here. But if r equals 1, so in the special case r equals 1, this is one single function. So generally speaking, for this special case r equals 1, we call this the scalar wavelengths here. But for some simplicity, in this talk, we are going to just using so I'm going to ignore this. So do not make any distinguish the multi-wavelengths and the wavelengths here. For all R, we just call it the Reitz wavelengths here. So why the Reitz wavelengths in the Sobolev spaces is interesting? Is because it's a very simple facts here. So if you are going to have this, so because m equals 0, this in the L2. So if this is a Reitz spaces in the L2R, then quite often, so this means if m equals to 0, then this factor is gone. But by a very simple scaling of this one times this factor here, so this ASM is often a Riesz basis in the Sobolev space HM for m in a small intervals here, including, so let me draw the graph here. So basically you have alpha here, you have a beta here, and 0 sit in the middle here. So for the range from alpha to beta, then this system form a Riesz basis in the Sobolev space. So this means starting with waveness in the square integrable function space L2, then by using a simple scaling, then you are going to get the Riesz waveness in the Sobolev spaces for m on these intervals here for some number alpha and beta here. So the major problem is here how we are going to construct Riesz waveness in the Sobolev spaces. This is coming from the bi-orthogonal wavelet construction here. So what is the bi-orthogonal here? So the bi-orthogonal is nothing else. We have two sets now. So we have this phi and psi in the Sobolev space HM, but we also have another part. So the other part is the bi-orthogonal part, or sometimes called the dual part. So the dual part is very similar. So now you are going to have a phi theta, and you also have a psi theta here, but you have to pay attention. So the phi theta and psi theta is in the dual Sobolev spaces. So pay attention to the negative smoothness. So this one, H negative M, is a dual space of the Sobolev space HM. Then after we have a pair of phi psi and phi theta and psi theta, then we are going to get a bi-orthogonal waveness in a pair of Sobolev spaces. So in the negative exponent minus m and in the positive m. So this one is very natural now. So what we want this dual part generated Riesz waveness in the H negative m, and we're going to want this primal part is Riesz wavelet in the Sobolev space HM. So basically we have two Riesz wavelet bases. One is in the HM by this primal part, but we also have the dual part, which is in the dual Sobolev space. And the next requirement is that, so these two systems here should be bi-orthogonal to each other, because we want the bi-orthogonality condition. So once we have the bi-orthogonal wavelets in the Sobolev spaces, what we are going to have is that for any function f in the Sobolev space HMR, then we have the wavelet representation here. So f will be always can be decomposed in this way. And here you have to pay attention. So this is very similar. So if I'm going to take m equals 0 here, you are going to see this highlighted factor is gone and this is gone. So this is, so let me just write down here. So this f with jk, but with the third part. And you also have a phi jk. So this is often the classical wavelet representation in the space L2. But if you are going to deal with the decomposition in the Sobolev spaces, then you have to regard this one as one element. And then you also regard this one as one element here. And it looks like quite trivial because this factor have a negative sign, this have a positive sign, they're going to cancel. This times with this is just 1. However, the most important thing you are going to see the 8, so these elements in this space HM. So if I'm going to calculate the norm of this whole thing here, you are going to see this is uniformly bounded in the HM norm. And similarly for the dual part, so for this dual part, if you regard this part, and you are going to calculate the norm in the H negative M, so means this space, H negative M, then this part is also uniformly bounded. So for many applications of the wavelengths here, there is a very important property called vanishing moments here. So basically, you can most of the time I write as the polynomial x to the power j, and the inner product with phi, and this vanishing. So you want the inner product between the polynomial x to the power j and the psi itself. They should be perpendicular for j sufficiently large. So for the numerical PDEs, in order to solve any partial differential equations, then we most of the time we are going to use the bioorthogonal wavelengths in the HM. So if you are interested about the bioorthogonal wavelengths in the Sobolev spaces HM, I think I addressed this issue in this paper. So a major problem, a very important problem is that this is a bioorthogonal wavelengths on the real line R. So in order to solve the problem, we are going to need wavelengths on a bounded interval in the Sobolev spaces. So what we are going to do is how we are going to construct such wavelengths in Sobolev spaces. So in order to do the construction here, we have to start with the construction of the wavelengths in the L2. So what is the bioorthogonal wavelengths in the L2R? How we are going to construct this one? For this one, we have a necessary and sufficient condition. So if we are going to have this, a pair of this one is a bioorthogonal wavelengths in the L2. So this just means the linear system, so corresponding to M. So pay attention, M equals 0 for both cases. So this system and this system forms a bioorthogonal basis of L2. So this system here, once again, is a translation of the function phi, and this is a standard one. So just this in the L2, because we're dealing with the square integrable function spaces. So any bioorthogonal wavelengths in L2 must coming from these three conditions. And for sure, the function should belongs to L2. So this condition is just a normalization condition. And so for the psi and psi theta, so this just the vanishing moments one condition, because what we are going to take is so for this polynomial, if j equals 0 here, this polynomial is just 1. So this just means you must have the vanishing moments at least 1 for both psi and psi theta here. So the next one, so the phi and phi theta should be bioorthogonal to each other. And how we're going to construct this one? This one must have the field bank. So this notation, so L0 just means a sequence of finitely many non-zero coefficients on certain integers. So this notation just means is a sequence. So from G to R. So basically means you have a sequence here. And for this sequence, you have only finitely many non-zero here. And then you are going to see the function phi must be refinable with a mask A or filter A, and its dual function is also should be refinable, but this time you must use the mask A theta. So the wavelength psi is derived from the refinement function phi using another different filters and the same phenomenon as phi theta. So not only here, so the four filters, the A theta and B theta here, they must satisfy this bi-orthogonal wavelet field bank condition. So what is the notation of this A hat? A hat basically means because A is a sequence, so A hat is just a two-periodic function, and with its coefficients AK from the sequence. So you are going to see how we are going to construct bi-orthogonal waves here is quite simple now. So what we do, we basically starting with this. So we are going to construct A and A theta, and as well as B and B theta. This satisfy this condition. So after we have this one, then we go up. Then we're going to get a function phi and get the function phi theta. And once phi is given, then we can define this psi using these two conditions. And so this 1 and 2 are technical condition. And so you need the most important condition you need to check is this. The function belongs to L2. Because this result is a necessary and sufficient condition. So this gives you the general construction, how to construct bi-orthogonal wavelets in the square integrable function space L2. So this one tells you the construction of bi-orthogonal wavelets in L2R generally is quite simple due to this very nice condition you need to check. So the next issue here is once we have the wavelets on the real line, then you have to adapt this one to the bounded interval. And for this one, how to adapt wavelets from the real line to this interval from 0 to 1, because we are going to use a tensor product wavelets here. So we only need to adapt the wavelets from 0 to 1 and then use a tensor product. And this one generally is a very challenging question. So, and before we talk about, let me emphasize here. Here we only consider the tensor product domain. So tensor product domain basically is in every dimension, this in intervals here, then you just form the tensor. And so this how come if we are going to illustrate using wavelets to solve numerical PDE with a domain, for example, domain looks like this. This is not a tensor domain. And if you want to build wavelets on this domain, generally it's a very challenging question. I'm not saying that this is not possible. And this is possible, but you have to do a lot of work. And the construction generally is very complicated. So just how come I don't talk about this issue. So, but the problem is a lot of weak solution U is in the Sobolev space. So not only in the L2 space. So how are we going to obtain the wavelets in the Sobolev spaces in this Sobolev space, because of the omega is domain now, not on the whole space. But what we want in order to solve the numerical PDE, we want to build the wavelets in the Sobolev space in this space. So what we are going to do, we starting construct wavelets in L2, and then we can easily show that after a very simple scaling, then so you are going to see we are going to construct a compactly supported bi-orthogonal wavelets only in L2. Okay, it's very important. Not only in the L2, you need some two conditions in order to achieve our goal. So our goal is wavelets in this space. So the two condition is the function phi must belongs to the Sobolev space HM, and this is very natural because what we want is we want this both phi and psi should in the space HM, and because the psi is, so if you go back, so because the psi is completely determined by phi. So if this phi belongs to HM, then because this is a finitely supported sequence, then the whole finite linear combination also belongs to the HM. So that's how come we only need the phi belongs to HM, then we automatically obtain that the psi also belongs to HM. Now, not only here, and it's very important that the wavelength function psi, they must have eventual moments for sparsity, not only for the sparsity here. You are going to see, in order to use wavelengths in many applications, the wavelength function should have a vanishing moments. So just how come we need this two condition? But this is fairly relatively easy because you can use a relatively smooth function to achieve this condition. So the vanishing moments for psi is also very easy to achieve. So this both condition can be easily to achieve these two conditions. So after we have this one, so the most challenging part is this. So we are going to adapt the bioorthogonal wavelengths from L2R to the L201. So this is a unit in intervals here. And not only here, in order to solve numerical PDE, we have the boundary condition. So that's how come we have to consider some desired homogeneous boundary condition. So sometimes we don't need any boundary condition, but sometimes we have to impose, for example, uniquely zero boundary condition. So you have to also achieve this goal. So after we have this one, then we need we are going to build a wavelength from the L201 to the subnet space. And so you can, once you have the one-dimensional wavelength from the L201, then using tensor product, you can consider any domain from, so that's how come the domain is from 01 to any dimension D. And then we have a general theory to guarantee from this to this is very simple, by a very simple scaling. And so basically 3 steps. This is the first step, this is the second step, this is the last step. I should mention that, so generally one has been extensively studied in the wavelength literature. So generally one is not a problem. So for the step 2, how we are going to adapt the wavelengths from the bioorthogonal wavelengths from L2R to the bounded interval 01, this problem have a much less work. So as far as I know, I think Wolfgang Dahlmann, he has work to adapt a bioorthogonal scalar wavelength. So means this have a function. This is not a vector. This is not a vector here. For not only scalar, indeed, the paper he has is require this one to be sparse. And this, and also the construction is very particular, and indeed is very complicated. So that's how come, even though in my opinion, even though wavelengths for numerical PD has been studied many years, but still the progress is not that great. It's basically because the step 2 is only solved very recently. So I solved this problem for quite many years until the step 2 is completely resolved. So the last step is so basically there's some work also by Wolfgang Dahlmann. He put several Jackson-Bernstein inequality, and then he can show that if you are going to have a wavelength from L to 0, then they can you are going to get this wavelength in the subnet spaces, but you must require some conditions. A lot of technical conditions. So to check the Jackson inequality and the Bernstein inequality. So Jackson inequality, generally speaking, is relatively simple to check, but the Bernstein's inequality is very hard to check. However, at this moment, this step 3 is also can be easily proven now. So after we have the wavelength and the bounded interval, you can use Galerkin, or you can even use a collocation method to solve the boundary value problem. Because this part is generally speaking is a little bit technical, so I only gave you the key idea. So what we are going to do is from the wavelength on the real line, we have a very relatively simple approach. We call it the direct approach. So basically, we're starting with wavelength on the real line in the space L2R. And then we are going to use a direct approach so that we are going to construct wavelengths on the interval 0, 1. So you are going to see the wavelengths will. So you are going to see the wavelengths will be looks like this. So in the intermediate part, so this is the intermediate part. This looks exactly the same. So the middle part. For this domain and for the real line, so this have no difference. So basically, if you have wavelengths on the real line, if the support also fall into this intervals here, you are going to keep them. So the complexity coming from because this domain have two endpoints. 0 is the boundary points, 1 is the boundary points. Then you have to design the boundary from the left boundary, right boundary, as well as for psi. Also so basically this corresponding to the endpoints 0, this corresponding to the boundary 1. So the difficulty is a boundary 1 you have to design. Now at this moment, now we have a very simple way to indeed construct this boundary condition so that they can achieve. So this all the boundary waves here now have the same order of vanishing moments as the interior, the mother waves side here. We can achieve this. Not only achieve here. And such waves here. So this boundary waves here not only should have the vanishing moments, but also this kind of waves here, all of them, this side, they have to satisfy the given boundary condition for all of them. So this part and this part, all of them they should satisfy the boundary condition. And the most important thing is for this general construction, we never explicitly compute the dual. So this is the major difference. Why we are actually call this one as a direct approach. Because the most important part is this part. And for numerical PD, this dual part never explicitly appear. So that's how come this construction never using the dual. Okay, so this general approach. So a little bit more detail. I just so all the detail is already in this paper here, published 2 years ago. So generally speaking, the construction and the rough idea of the construction looks like this. So instead of consider the interval from 0 to 1, you are going to consider 0 to infinity. So one side. So because you just have only one endpoints here, Then you are going to construct this phi L, so that all this of them will be sit here, and construct this phi L. Generally speaking, is quite simple. So this phi L boundary one is very simple. So the most difficult part is the wavelength part. So this wavelength part here, you are going to see we can require this phi L to satisfy the boundary condition. And if you have a boundary condition, you also have to make sure this satisfies the homogeneous boundary condition. And how we're going to construct this psi L, and indeed this is coming from the linear combination of phi L with the sum of this touches the boundary. And also you have to make sure this boundary psi L is the basis of some individual complex spaces. So after you have this one, then you are going to theoretically you can compute finite matrix here, and the condition is quite simple. This finite square matrix here has a spec radius less than this. If this condition is satisfied, then this phi delta and psi delta and this one forms a orthogonal wavelengths from 0 to infinity. And so after we construct the wavelengths on the positive axis, then we also do the construction from negative infinity to 1 here. But this is quite simple now, because you can do a very simple flip. So if I'm going to flip this, then you are going to get from negative infinity to 0, and then an integer shift tells you from minus infinity to 1. So this one will complete that. So the main idea of this one is generally simple, but you still need to do some work. So after we are going to adapt L2, we are going to get the wavelength basis on the interval from 0 to 1. Then we can use the tensor product here. So the tensor product is always looks like this. So there's no problem at all. But in order to solve the second order PDE, so what we want wavelengths on the subnet space H1, the M equals 1 here. So now we cannot just directly using the wavelengths in the little L2, which we already construct here. So how we're going to prove any wavelengths in this L2 will form Riemann spaces in the subnet spaces, and this one we have a general theory to guarantee that this condition is always true by a very simple scaling. So I'm going to talk about this. So now let me starting with the two problems. One is the wavelength method for the large cavity problem. So the cavity problem will be looks like this. So the problem domain is basically not finite. So it's from all the spaces. This is a whole space, because this domain is not bounded. So generally speaking, so this one is a PDE. So this is a Helmholtz equation. So and the domain is so this omega refers to here. So in order to solve this problem, then you have to change because this original domain is on this whole space. So you have to add this line and then translate the problem outside one into this nice domain. And because this is unbounded, so if I'm going to transform the information outside into this square, so this how come you are going to have a non-local operator. So this T is very complicated regarding with the Hankel integrals. So because your information, all the information will pass through this line. So this how come this side. So let me redraw it here. So this edge is very common, is gamma here. But for the problem beyond this gamma here, so the boundary condition generally the zero unique boundary condition. So because this line corresponding to the Earth's surface, this underground here. So this little square is underground. So the boundary condition, you are going to have this zero boundary condition, zero boundary condition, zero boundary condition, and because this side is a dynamically boundary condition. So which kind of wavelength you are going to need is the wavelength has to satisfy the homogeneous dynamically boundary condition, zero dynamically boundary condition on this side, and dynamically zero boundary condition, but this side have no condition. So for this gamma here, you don't have any condition. Because we are going to use the tensor product wavelengths here in order to solve this problem. So the Sobolev space we are going to consider is this, because you only have this side have a dynamically boundary condition, this side gamma have no condition. So this Sobolev spaces. So if I'm going to use wavelengths, tensor product wavelengths to solve this problem, so you are going to see if you do this direction, so you are going to have the zero boundary condition, zero boundary condition. So you need one type, zero here. But if you go to the vertical direction, now it's a little bit weirder here. So this part need a zero boundary condition, but this side, so touch the top, you don't have any condition here. So the top one have no condition is free. So the wavelengths we are going to use here is both satisfy the zero condition. So that's how come. So you are going to see. So for this one, so basically this corresponding to the horizontal one, you need the zero dynamically boundary condition, but for the vertical direction, the y direction, you only require the dynamically condition here. So, and for this one, the weak formulation of this problem is given by this. So after we have this one, so then the major problem construct a wavelength from 0 to 1 is fairly simple. So construct this one in L2 and also in L2, both of them in 0 1 0 1. This have no problem. Satisfy this boundary condition, and then we need to prove that. So whether this kind of things now can become the risk wavelength in the one-dimensional problem. So because we first have to show them, and this is indeed fairly simple. So if you are going to have a biosonal wavelength in L201 in 1D case, so how you are going to form the risk wavelength in the Sobolev space here is nothing else, is a very simple scaling. So as a core scale J naught, you just have times this 2 to minus J naught. So for the psi j, you are going to have the scaling 2 to the minus j. And then the theory actually with a relatively simple proof to show that by this very simple scaling, then you are going to see any wavelength in this Sobolev spaces. So you have to regard this as a one element, because this scaling 2 to the minus j, 2 to the minus j, and then this function in the Sobolev space H1 norm now is equivalent to the L2 norm of its coefficients. The C, so this is the little L2 norm. So have a norm bound upper bound. So this one shows this one indeed. So forms a Riesz species. Hello? Hello?
Yes, sir, we can hear you.
Okay, good. So what I'm trying to say, if you're going to have a wavelength on the real line in L2, then the most difficult part is that you are going to adapt this one to the bounded interval 0, 1 in this space. After you have this one, then to get this wavelength in the Sobolev spaces is quite simple, just a very simple scaling, and the proof is quite relatively simple now. And because our goal is trying to get 2D, because this problem is a 2D problem, so we have to use the tensor product. We here, so the tensor product is very simple. Everything in, now pay attention, everything in L2, okay? So in this L2, so this tensor here. So after you do the tensor product, so what we want the wavelengths in the Sobolev spaces, and this can be easily done. So because using tensor product of wavelengths in L2, then we are going to get a 2D wavelengths in L2 0, 1 square. Then how we are going to get this Riesz spaces in the Sobolev spaces is nothing else. It's very simple now. Even in 2D, the scaling factor is still the same, 2 to minus j naught and 2 to minus j. It's no longer square because we basically deal with H1 in the domain, in the 2D domain. So the factor is still the same. And after you have this one, you have to regard this as the whole one element. The reason is also quite simple. So if I'm going to calculate the H1 0, 1 square norm, then this is uniform bounded. Then you are going to see the H1 norm in 2D and is equivalent to the little L2 of the coefficients here. And this is also rigorously proved. Okay, so after we have all the wavelengths on the bounded interval in the Sobolev spaces, now we can play around. It's very simple. So what we are going to do, how to construct the biorthogonal wavelengths from the Hermite cubic spline. So it's low pass filter for this Hermite cubic is given by this. So this for the Hermite cubic spline. So how we are going to do the construction? The procedure will be looks like this. So this is given here. So after you have this one, so then you are going to construct a biorthogonal low pass filter, A tilde. So A tilde is biorthogonal to A. You have to construct this one. This is a little bit technical, but this can be done. So after you construct A tilde biorthogonal to A, then you can derive from the A and A tilde here, from A and A tilde, then you can get this B and B tilde. So basically B and B tilde derived from A and A tilde here. So this whole thing here, so if you go back, this for filter will satisfy this technical condition. So it's this satisfy this condition here. So this part is relatively simple to do the construction. So this shows indeed we can relatively easy to construct wavelengths on the real line in L2. So after we have this one, then we can adapt such wavelengths from the cubic Hermite cubic one on the real line. And so I only show some plot. So this is the Hermite cubic function, and this is psi. And so the dual, generally speaking, the dual generally is very weird and very complicated, and the smoothness, generally speaking, is low. So this part is the dual phi theta. This is psi theta here. And generally, if you pay attention, the support, generally speaking, is none. Both of them are supported from -4 to 4. And they don't have any expression, but this phi and this psi, they are splines. I mean, they are piecewise polynomials here. So if you're going to adapt the wavelength to the bounded interval here, so you are going to do this for the left boundary because our model is from 0 to 1. So you are going to see if you are going to don't impose any condition, then you could take this. So they are not vanishing here. But if I'm going to impose the Dirichlet boundary condition, this is also possible. So that's how come. So for this phi L, so you are going to see we have 3 components now. So you are going to see the black one, the blue one, and the red one. So you are going to see 2 of them vanishing here, vanishing here, but this one does not satisfy any boundary condition. So that's how come this one does not require any boundary condition. But if I'm going to impose the boundary, the boundary condition, so what is the boundary condition? Is we want this function LBC at the 0 should be 1. So all the functions should vanishing at the point not 1. Should be vanishing at 0 here. It's possible. So you are going to do this the 3 components now. They all of them they are vanishing at the satisfy this condition. So not even here. Sometimes we even have not only require this one vanishing, and we also require sometimes require this derivative vanishing at the 0 here. This is also possible. So the plot is given here. So this have a no boundary condition. This have a Dirichlet boundary condition. This 1 level higher. So you can do the construction, and the construction is relatively simple. So also for sure you can do the same. So for this one is a synod spline. So this is phi. This is the psi part. And for this one, the dual is relatively simple, but the support generally is none. The construction is always the same. So you are given A here, so you are going to construct a theta, and then obtain the B and the B theta. So you are going to get the wavelengths on the real line. Then you are going to adapt them to the bounded interval. So this is the boundary phi L. This boundary psi L, so there's no boundary condition, but this one have a boundary condition. So the wavelength is vanishing here. So the construction is no longer adapt the wavelengths to the bounded interval, and to prove they form Ricci spaces in the Sonev spaces. It's no longer a problem, just a very simple scaling. So this is the 2D elements. So form for using that tensor product. Now, how to solve the problem here? So we are going to compare. So if I are going to using the so-called only using, so our wave basis is given by the B3J. So what is 3? 3 stands for the cost scale is little j equals 3. Go to the little j, go all the way to the capital J. So this cost scale is from 3. So this is a lowest. So what is the finite elements method here corresponding to this? If you're only using this phi j, so-called refinement function, this is the popular finite element method here. So if you only using phi j, so the most important thing you also pay attention here. So this is the basis. This is also basis. Not only here, they generate the same space. So let me write down here because it's fairly important. So if you're using the linear combination here, so using the span, So the span by this 5J or the Wayne basis, they basically span the same space. So it's not as surprising. So the the solution you are going to get using the wavelets or using the finite elements problem, because the space the space generated by the wavelets or generated by 5J, they are the same, and therefore the numerical computer solution, they are the same, and as a consequence here, so if you pay attention, you are going to the error is pretty much the same. So you can see this, so they're the same, and this also the same, because the space they are the same. So what's the difference here for the Williams method here is once the level J is so means the J becomes larger and larger, the matrix becomes larger and larger. If you are using the finite elements method to solve the problem, the continuum number could be huge. But for the Williams method here, the continuum number basically stays as a constant. So if you are using the continuum number of the finite elements over the continuum number, Cn stands for the continuum number. So the continuum number of the Williams, if you take the ratio here, you are going to see at this level is 800, over 800 larger than the continuum number of the Williams here. And not only here, if you are using another different wavelengths here, so the same phenomenon, so you are going to see using the finite elements that the continuum number becomes much larger, but the wavelengths becomes basically is uniform bounded. And some of you will see why. So you are going to get the same solution, and the continuum number wavelength is smaller, and the finite elements will always increase. Why? The wavelengths really have the advantage. This is coming from here. So for the Helmholtz equation, if the wave number kappa is large, then generally speaking, there is a well-known condition. So the mesh size h times the wave number kappa, this should be at least less or equal to 1. And you cannot anything not satisfy this condition, the solution you computed does not make sense, because it's very understand the Helmholtz equation is a sort of wave, looks like this. Once you have a wave, then your mesh size has to be small in order to capture the highly oscillating solutions. You must satisfy this condition. So if you're going to solve the Helmholtz equations, then you are quite constantly to see the problem of the size of a linear system generally is very large. So basically, essentially, you are going to solve this linear algebra problem AX equals B, but this A is a very large matrix. So if I'm going to use a direct solver, and this generally is not possible, so the most popular one is you are going to use an iterative solver to solve this problem. And if I'm going to use an iterative solver to solve this problem, then it's very important the continuum number have to be small, because if the continuum number is very large, then the iteration will be much larger. I mean, if I'm going to use an iterative solver, then you need to compute many steps. So that's how come the steps, the continuum number is very important. So that you don't do too many iterations, and this is very important for the Helmholtz equation, because iterative solver basically is the only choice. And also this same phenomenon, so I'm going to skip. So this one is we are using the iterative one. And so for this kind of a problem here, because wave number you are going to see is looks like not large. So if I'm going to use an iterative solver, then you are going to see as j becomes larger, then you are going to the iteration for this one generally is quite stable. So you don't need to the iteration number to achieve the target accuracy is the iteration number generally speaking is relatively small. So if you look here, it's also very small. The reason is because the Canadian number is uniformly bounded. So your iteration don't go. You don't need many iterations. If you are using the finite elements problem, so you are going to see the iteration is generally very long. I mean, so that's how come we don't list what is the iteration corresponding to the finite elements method here. Okay, so you can see. So this is a finite elements method here. So this is level of j. So if your j become larger and larger, so you are going to see the iteration becomes larger. And if you're using the waves here, so you are going to see basically once the j is large, it's basically more or less the same. So this iteration regarding of how large is j, the uniform bounded, but for the finite elements method here, so if j is large, then the iteration number will be much larger. And this also another one, so it's 32 pi, so basically it's around 100. So you are going to see for 2D, even for 100 problem, then you are going to see the mesh size, generally speaking, have to be small, and all the linear system is very large. So using wavelengths to reduce the continuum number indeed is fairly important. Okay, so I will. So you can also do so this one is more or less same. So it's so this just the only difference is that this is not this Hermit cubic. So basically they have the same phenomenon as way before, and also it's very easy to see. You are going to see the iteration is always stay the same. I mean, they don't significantly increase, and they are generally speaking is much smaller. And for this finite elements here, we are not even so. Even for this wave number, we don't provide the iteration number is because the iteration have to iterate so many times. I mean, it will take 1 day or 2 days in order to compute them. So, and the iteration number is huge. So just how come we didn't apply the iteration number here. We only for the wavelength method, we provide the iteration number part of it. For the final one, the generally is huge. So that's how come. So now let me spend the last few minutes to another kind of problem, derivative or second one. So the goal is always we want the wavelengths in the subnet spaces. So our previous construction is always constructed in L2. So the question will be, can we directly construct wavelengths in the subnet space? So instead of goes to L2R, and can we directly do the construction in the subnet space HMR? Not only here, we also need the derivative of second one. So derivative is not derivative in the m equals 0 here. You take the mth order derivative, mth order derivative. This kind of things they are have the also linearity condition, and this one indeed instead of construct waves in the ozone, for example, for the ozone waves in L2R, and construct, if I just directly jump to the subneft basis, indeed the construction is much simpler. And the theorem says that in order to construct waves in the derivative orthogonal, so we not only reach waves in the HM, but we also require the derivative orthogonal one. So derivative orthogonal one means this property. So you are going to see this. We also have a necessary and sufficient condition. The condition is so weak. So you are going to this condition is just a determinant non-zero condition, and this is very easy to be satisfied. So the only key condition is this condition here. So, and as long as you can construct B, so because A is given, you only construct this BM, but this linear system, B only appears here, B only appears here, this linear equation to solve this problem. Then you are going to automatically get the Rees waves in the subneft spaces. So that's how come for this one, the construction indeed is relatively simple. So let me give you one example for the Hermite cubic spline. M equals 1. So this is the A. So you are going to see the no. So you never deal with. So just how come you never see this you don't see the A tilde, you don't see any B tilde, you directly construct B. Then then after we have this B, so just after you construct this B, then you automatically get this psi. So once we have this B here, then this is the derivative orthogonal one in the Rees subneft H1R. So this cubic spline, and this is psi. So the construction is much. So if I go to for the Hermite cubic spline with M equals 2, you even see that the B is so simple. So this is still the same mask for the Hermite cubic spline. So the filter B is fairly simple, only one term. So this is the Hermite cubic spline, and this is the size. So how we are going to obtain this one? Because this is just half. So then basically you can obtain the form here by just shrink them by half. So and then you are going to see this is very similar to this. So that's how come the advantage of this derivative orthogonal one is the construction is very simple, and you are going to directly jump to the subneft spaces. I should warn you here. So this kind of Rees waveness is not Rees spaces in LR. Generally, is not true. Okay. They not form Rees spaces in little L2, but they form Rees waveness in the HR. And for sure, you can apply to many different examples. You can see the very similar phenomenon, a very simple mask here. So we only did this one for the 1D differential equations. For example, if we are going to solve this 1D Poisson equations, then we can use the Galerkin scheme to solve this problem. And so the most interesting thing here is so using the Galerkin scheme. So what is this? Kappa is not a wave number. Kappa stands for the conditional number. So what is the conditional number? Is will be exactly 1. So what this means? Because we have the derivative orthogonal waves here. If I'm going to form the linear system to solve this problem, so what is A here for the using this particular derivative orthogonal Rees waves here? This A basically is the identity matrix. You don't need to solve this linear system. So that's how come my explanation right here. A is the identity matrix here because we have the derivative orthogonal one. So the waves are given here. This is a boundary. This is the interior one. Because the derivative orthogonal one, so clean number is 1. You don't need to solve the linear system. You can get the solution right away. And you can also solve for the fourth order scheme. They call it biharmonic. Even using this alpha u, you can solve this problem using the Galerkin scheme. So if you're using, so once again, you can using the Hermite cubic spline with the tau because the wave bases are very simple. So I would ask you to look the Canyon number. So you are going to the Canyon number is so close to 1. So that's how come the derivative orthogonal one indeed have two advantages. The first one is that the construction generally is very simple. The second advantage is the generally speaking, the Canyon number generally is relatively small. So that's how come I think if I'm using such wavelengths, such tensor product derivative orthogonal one for the 2D problem, then generally speaking, they have a simple structure, and the Canyon number generally speaking is relatively simple. So you can also do the biharmonic without the alpha u. So if you solve this one using the Hermite cubic, so if you are using the Hermite cubic with m equals 2, so for this one, once again, because we don't have so let me go back. So we don't have this term, okay? Biharmonic, we don't have this term. So for excuse me. So for this one, the biharmonic equation using the Hermite cubic one, the Canyon number still once again is equals 1. So the linear system we solve, I'm using B here to distinguish. So this matrix P here is identity here. Even for the biharmonic equation, you don't need to solve the linear system because this identity. So let me finish my talk. So what I'm trying to pass to you the information here is just two sense. So the first one is any complexity supported by orthogonal waves on the real line can be adapted to the Sobolev spaces, provided that the domain should be tensor product. So what is the tensor product? You have so in 2D, it looks like a rectangle. This is a tensor product. Not only here, in 2D, you could use polar coordinates. So if I use polar coordinates here, this becomes underpolar. Then this one will also so is a tensor product domain. So then we can always build for the tensor product domain. We always have the wavelength basis satisfy the desired boundary condition. And so the advantage of the wavelengths generally have the small condition number, and they have a sparse coefficients here, and the continuum number, and both small continuum number and the sparsity, they are very suitable for the iterative solvers. And for the derivative orthogonal wavelengths here, generally the advantage is that the construction, we directly deal with the Sobolev spaces. The construction is simple, and generally the continuum number is very small. So the last sentence, I would like to say that this is a very classical wavelength method to solve PDEs. So a major problem I'm thinking about is what is the unique advantage that the wavelengths can solve the problem, but other method may face a lot of challenge. This is related. So that's how come currently we are using the wavelength method to to solve the elliptic interface problem. I believe for this problem, we must have a very clear advantage to solve the elliptic interface problem. So if I using the finite difference scheme or the finite element method to solve the elliptic interface problem, generally speaking, they have several difficulties, but the ways to solve the elliptic interface problem has a great advantage. However, for this last icon here, you cannot use the traditional wavelength method to solve the elliptic interface problem. You need some new, you need to change the main idea to solve the elliptic interface problem, because we haven't finished this project here for the elliptic interface problem. So I want to talk about in this talk. So basically, this is my talk. So if you have any question, you can talk to me. So thank you.
Thank you so much, sir, for joining us in the meeting today and for these enlightening words, which were quite informative and interesting to listen to simultaneously. Last but not the least, if any participants have any insights or queries, you may freely ask sir regarding these. Does anyone have any doubts?
Good evening, sir.
Yeah.
Sir, can we solve uncertain the system with uncertainty?
Which one? Which page?
So no, not about any page.
Yeah.
I'm telling that if the system had some uncertainty is added. Then,
Uncertain. So by what do you mean uncertainty in the?
Uncertainty means, sir,
Yeah.
sometimes the parameters are, suppose sometimes the parameters are coming some value. Then due to some condition changes, some uncertainty are also added, na?
Oh, so you mean you once you solve the problem, you have a certain kind of parameter which you don't know, but you want to solve the linear system.
Yeah.
So if you have uncertain parameters in the linear system, and I think quite possibly if you are using direct solver, you are going to run into trouble. But if you are using the iterative solver, probably is a better way to go. So basically it's related to this problem, how you are going to solve this problem. But you can write this one using sort of how to say this. You could write this as for example, you have x and plus you have a. So this naive iterative solver. So you have x plus a minus I times x. Definitely this gives you the same as a x here, right? So if I'm going to write, so then you solve this one as x equals b minus a minus the identity and x, right? It's the same. So
Yeah,
in order,
yeah.
so this is the same equation. So now if I'm going to solve them, then you are going to solve in this way. So it's a b minus a minus identity and xm. So you're starting with x naught, for example, is a 0 vector here. Then you using this iterative one, and then you hope this xn converges to your solution, right? And then if you have any uncertainty about a, then this won't affect this iterative scale. right?
Mm-hmm.
So that's how come intelligent solver could be a way you can consider. And this is why for the Helmholtz equation, this linear system AX is huge. And if you look the problem I'm talking about, the wave number, the people generally handled. As far as I know, for all the people I read, the most largest wave number people can handle is 400. And this is because and how large is this X here? This generally is one at least over millions. This one generally is the size is at least 10 to 10 to power 6. Even for the problem we solve for 100, the linear system we handle is already that large. So it's a million by million. If you're using direct solver, and then general scheme is very hard. So that's how come why I say for the Helmholtz equation, wavelength is very important, is because this matrix here is huge, and the only possibility to solve this problem is this intelligent scheme. So this intelligent scheme requires this A must have a small Canadian number. And if A Canadian number is large, then this intelligent scheme conversion is very, very slow. Right?
Okay, sir. Thank you.
Okay, you're
Hello,
welcome.
sir.
Yeah.
Sir, Professor Han, can your problem solve non-uniform tensor product things?
Oh, so you mean whether wavelengths can be
Masses are non-uniform tensor products.
Yeah. So we are doing. So the problem is coming from here. So basically here I should mention that in the literature, if your domain is not a tensor, so basically if your domain looks like this one, and if you want to construct the so if I'm going to solve, yeah, I don't know where the noise coming from. So I should mention that if your domain is not a tensor product, waves can be constructed on such domain. However, why the construction of waves on the boundary domain is very hard. You have to understand why it's so hard. So let me give you the example even in 1D. So why the waves adapt to the boundary interval is hard? It's basically because waves have a multi-structure. So you are going to see the waves generally have a lower resolution, looks like this. And then once the resolution is higher, then they have a support is smaller and smaller, right? And then what you are going to do, this is your domain. So for this one, you are going to this level. So you are going to have a boundary here, at this level, for example, this level 0. Now, if I'm going to get every single level, for example, this is 5, then you also have a boundary here. Also have a boundary here. So what this means, for any j from 0 to the capital J, so you have the boundary waves here. You have to at least 1. So you are going to how many waves elements here? You have at least J plus 1 here. And so because every single have the boundary. And also you have this side. So the total at least you are going to have that many boundary waves on both sides. But once J is large, then the boundary waves touch so the waves touch the boundary so frequently. And that's how come makes the construction of waves on the boundary interval scale is very hard. So if you are going to have a domain looks like this one, so the same phenomenon. So for every single J, So you have a lot of things to touch the boundary at every resolution G here. Then you are going to have many boundary elements here. So this how come make so if your domain is not a tensor product here, then the wavelength near the boundary is very complicated. But if you're using the finite elements here, then you are going to because they have one size. So for the finite elements here, so you are going to have a boundary here. So if I'm going to compare the finite elements here and the wavelengths here, you have a much more boundary wavelengths in this situation. So if your omega is not a tensor product domain, then the construct wavelengths for non-tensor product domain generally is very challenging. Not only very challenging, even you can construct such wavelengths on this domain, then your implementation generally is much more complicated. So that's how come we only deal with the tensor product domain instead of general domain. I mean, even you can construct wavelengths in this domain, in this non-tensor product domain, but the implementation will be very complicated. So that's how come at this moments I only consider wavelengths on the boundary domain. And if you are going to see where my problem is not the tensor product domain, so can we use the wavelength to solve this problem? The answer is yes. This is because so let me using a space. So for example, if you have this L shape, okay, this is not the tensor product domain. So if you're going to use wavelengths for this domain, then wavelengths alone cannot solve the problem. So you have to combine the wavelengths method with other kind of ideas. For example, you can use the domain decomposition method. So for this one, what you are going to do? Well, you can cut this one into this. This is a tensor product domain. This is a tensor product domain. So you have and plus the idea of the domain decomposition to solve this problem. Then if your domain is not a tensor product domain, you can still apply the wavelengths to solve the problem, but you have to use extra ideas to solve in order to help with wavelengths to handle this domain. So you cannot directly use wavelengths to solve the problem in this L shape. You have to use some other kind of. So basically, what I'm trying to say, you have to decompose this omega into a union of some tensor product domain, and then you can apply the wavelengths to such domain. So this is one answer. So another answer here is so another answer will be coming from here. So let us look some domain looks like this. So this domain is not a tensor here, but you could found some mapping here. So I shouldn't let me using eta here. So if I'm going to use a very nice mapping here, map this into a tensor product domain, then you can also apply the wave method here. If you can use a map from here into a tensor product domain, because the reason is that you have the wave set here, then you're using the inverse mapping. So you are going to have the wavelengths on this non-tensor product domain. So these two possibilities. Hello? Hello?
Yes, sir, we can hear you, sir.
Thank you, sir.
Yeah, okay, good.
Thank you again, sir, for your kind cooperation with us today. We are extremely happy to have you here with us today. Thank you for joining us today, sir.
Yeah, very nice to talk to you. Yeah, it's my pleasure. Yeah.
Yes, sir.
Okay.
So with this, yes, sir. With this, we have reached the end of our first session, and now we will be taking a short break of 15 minutes before resuming with today's workshop and starting with our next session. So, thank you, everyone. We request the participants to return after 15 minutes sharply to resume the remaining session. Thank you, sir.
Yes, yes.
Good evening.
Good evening.
How is Madras?
All right.
Can you show a view from backside?
Backside you cannot see anything. What
Huh?
is happening in house?
Office.
No,
Yeah.
I am not in the office. I am
So,
resident.
you're in office.
No, no.
knowledge and machines harmonize to compose our greatest innovations. Now, with this, we would like to begin our second session, which will be delivered by Professor A.K.B. Chansar of IIT Madras. Professor A.K.B. Chansar is one of the most honored professors of IIT Madras. He has been an epitome of inspiration to many of the students who have studied at Department of Mathematics, IIT Madras. In his span of teaching, which still continues with a glorious advent in his career, with an excelling career in life, he has done research on very important topics and currently doing research in domains of fractal interpolation, shape-preserving interpolation, and geometric modeling. He has an amazing array of research publication penned down with his name, generalized trigonometric interpolation, and iterative schemes involving several mutual connections. To name a few are some of his recent publications. We are delighted to have you among us, sir, and would like to invite you to his session to continue it with an amazing glimpse of your experience and knowledge. Sir, please. Sir, you can begin.
Yeah. Thank you, Simon. So I am thankful to the organizer, Professor M.K. Jena, and his colleagues for arranging this workshop. So I think now after this COVID, it is a new beginning. So start in hybrid mode or something like that. Okay, so today I'll talk about the application of these fractal functions in the other side of the research area. So that is the differential equations. My slide is visible?
Yes, sir, it is visible.
I think it has come something else. Just is it visible now? Yeah, so I'll talk about this fractal space solution to the boundary value problem, but here I have added the integral equation. So if time permits, then I will cover the last part of this fractal space solution of the integral equation. Otherwise, I'll stop for the fractal space solution of the boundary value problems. So my talk first, these outlines are like this. It is motivation, then basics of fractal interpolation theory, then generalized fractal polynomial spline, then cubic fractal interpolation function solution to the 2-point boundary value problem. Then there are some numerical results and discussion. Then one can go for this higher order smoothness. So in particular, one can go for the quadratic fractal solution of boundary value problem. Then we have given some examples where one can handle also non-linear boundary value problems. So then the fractal solution of the integral equations are there. So if you see the traditional interpolation functions, basically they are smooth or they are piecewise smooth. Okay. So to address the issue of producing very irregular interpolant, suppose you take any data from the stock market or ECG data or any very complicated function. Okay, so there you'll find everything is not smooth or piecewise smooth. In that case, actually, we need actually functions which are very wiggle or very irregular in the nature. Okay, so how to represent that function? Okay, the functions which are irregular, or you can say it is not smooth. Okay, a non-smooth function actually. So that can be approximated by taking the data points by using the concept of fractal interpolation. So this was given by Bransley in 1986. Okay, so he used the concept of the iterated function system. I will give the definition of little bit iterated function system. Okay, so then you can follow it. Okay, after that, Bransley also give the idea of whether you can construct a fractal function which will be differentiable. That means The nature actually, if you see the spline, it is or the function, it may be smooth, but if you see the derivative, it may be very irregular. It may be oscillate first derivative or second derivative or any depending on this r value of r actually. So that means rth order smoothness is there, but if you take rth derivative of that function, it will be like a continuous function which is not nowhere differentiable like Weierstrass function or Takagi function or different type of function. Okay, since we generate these fractal functions actually, because it is not an explicit function, this is implicit function, so it has to be generated through the given data points. Okay, so therefore basically we have to use the coding actually. So if you see the decimal system, they are actually dense in the real line. So therefore if you give any real number, I can approximate this by decimal system. Similarly, if you go for if you are using binary system, if you give any real number, I can approximate that by a binary number. Same thing will happen actually when you use the fractal function, depending on how many maps is there. So therefore each point in the real axis that can be seen as a n addiating number. Depending on that fractal code, one can evaluate what is the value of that function in a particular point. Okay, similarly, you will find the differential equation has been used to describe to model real life phenomena, or spline have been used to solve different type of OD, PD. Okay. So this classical cubic spline, this does not give appropriate solution if the non-homogeneous differential equation involves a continuous function which is not differentiable. Okay, so therefore generally this cubic spline is very popular to solve the differential equation. In the differential equation, if you find there is a function which is continuous but nowhere differentiable, because classical function, if you see any type of solution, basically they are either smooth or piecewise smooth. Okay, so therefore they cannot capture this irregularity which is coming from a nowhere differentiable function. Now this question is whether you can address this issue by using the fractal function. So therefore whenever you have the nonlinearity, maybe in the turbulence or ECG or any nonlinear data actually, so if you are modeling by OD or PD, if you are finding there is a function which is very irregular, then it is better to use the fractal function instead of using the classical functions, because here you can capture the irregularity very effectively. Okay, so what is the iterated function system? So you take a complete metric space. Dx is here the metric is there. Okay, suppose you take n number of continuous map. Okay, then if you take this space with n number of continuous map. Okay, so this is called simply iterated function system. Okay, so this was developed by 1980 by Hutchinson. Okay, so if each Wn here, okay, so they are contractive in the nature, so then we call this IFS is called hyperbolic. Okay, if each of this map is contraction, then it is called hyperbolic. Okay, so here if x is given, one can think of what is your h of x. This is the set of all non-empty compact subsets of x. Okay, so there one can define what is the Hausdorff metric. So like d of hx bc. So if you want to measure the Hausdorff distance between b and c, this is basically a maximum of these two quantity. Maximum of b belongs to b, minimum of c belongs to c, d b c, and maximum of c belongs to c, minimum of b belongs to b, d c b. Because these two quantity are not same in general. Okay, if b is contained in c, one of them is non-zero, another is zero. Okay, so therefore, so this is not going to be symmetric actually, so we cannot use this concept as the distance function here. So if you take the maximum of these two functions, then it is these two quantities, so then it will act as a metric here. Okay, so therefore, so if the original space is complete, okay, then this h of x, d of hx, this is Hausdorff metric, it is going to be a complete metric space. Okay, so therefore if each Wn here, if each Wn is a contraction map, okay, so then if you take this W as union of all these elementary maps, okay, n equal to 1, 2 and Wn b, so then this will actually, you can say this is a collage of n number of maps. Okay, so you are taking n number of maps, so then you will find W of b. This is going to be a contractive if each of them is contractive, and this contraction factor is the maximum of the contraction factor of Wn. Okay, so therefore if I is hyperbolic, that means each Wn is contraction, then this capital W is also a contraction, and this space actually, if the original space is complete, this space is complete metric space, and in case you have a contraction map, then contraction map in a complete metric space give you the fixed point. Okay, so that is your Banach fixed point. There are different type of fixed point theorems are there. So one can get the different type of fractals. Okay, so if you change actually the original space, and you can change the different type of fixed point here. Okay, so here there like mere clear is there, theta contraction is there, Binaki contraction is there. Okay, so several type of fixed point theorems are there. So now they are being generalized to construct different type of fractals. Okay, so in this case actually W is a contraction map, so therefore one can get the attractor here. Okay, and this attractor will satisfy this condition A equal to W of A. So this is equal to N equal to 1 to N Wn. So this is basically this is called self-similar equation, or it will preserve the self-similarity. Okay, so if whatever structure you are seeing of the entire object, okay, it is equivalent to this condition A equal to W of A, because W of A can be written as A again can be written as W of A. So therefore iteratively, if you see the zoom it actually, so in every part of A you will find the whole set is there. Okay, so therefore in factor we will get the self-similarity due to this property A equal to W of A. Okay, so this is the general fundamental properties of the fractals. Okay, sometimes they called actually this is self-similar. If the contraction factors are same actually it is called self-similar. If the contraction factors are different, they are called self-affine. So you'll get actually different type of these are this A actually. So this is called attractor or deterministic fractal. Okay, so therefore if there is a graph or anything is there, or there is a surface, or if any complicated image is there, so always it is possible to find suitable actually iterative function system and these elementary maps Wn, so that we can generate that one. Okay, so now this question is there. So when you are going to solve a differential equation or integral equation, okay, so we have to find the solution. Okay, so therefore the solution is nothing but there is a curve actually. Okay, so therefore how to get that curve? So this idea is whether what is called fractal function. Okay, so if you get some concept of fractal function, then you can use it and to find the solution of the differential equation. So that is our aim. So therefore I'll give the idea of what is the fractal interpolation. Suppose you have x and y n, so this is interpolation data. You know actually the standard interpolation like Lagrange interpolation or Newton divided forward, all these interpolations are there. They are global functions. Similarly, you can go for the splines or Hermite splines, or generally this big of Hermite splines, or maybe different type of like where deficiency lacunary interpolations are there. So there are plenty of trigonometric interpolation, hyperbolic interpolation, exponential interpolations are there. But all these functions are they are either infinitely differentiable or they are piecewise differentiable. Okay, here our aim is not to approximate such type of function. Our idea is to how to approximate the function which is like your Weierstrass continuous function, which is no differentiable function or something like that, similar to that one, or sometimes very similar to the stock market data or ECG data like that. Okay, so what we'll do here, you take the subinterval as in xn minus 1 to xn, and the whole interval I equal to x0 to xn. Okay, so one can think here, I think this should be capital N here, okay, because the last 10 point is a capital N. There is a typo here. Okay, so let k equal to I comma ct. So this y as this finite number of reals are given, so you can assume they are lying inside a compact set. Okay, so let you have n number of, because you have n plus 1 number of points are there, so here you need n number of, because this ln actually, so this will take care of the contraction in the x direction. Okay, so here actually if you see the fractal function here, so this is nothing but a graph actually. So this is a subset of R2. So therefore this fractal interpolation is constructed in H of R2. Okay, so therefore if you see the previous setting, here you take x equal to R2, here you take any metric actually. Okay, so this is R2 is complete. Okay, L1 or L2 or any metric, because all these metrics are equivalent in this finite dimensional space. Okay. So now you have, so this is the setting actually. In the x direction you are getting a contraction, in the y direction you have to fix another contraction map. So here fn x0 y0 equal to yn minus 1, fn xn yn equal to yn. Okay, in the y direction it will contract actually in the y direction. Okay, so this is the contraction factor is alpha n lies between minus 1 to plus 1. Okay, so therefore we got one contraction map in the x direction, another contraction map in the y direction. That means this fn actually what they will do, if you take any straight line, then it will compress by the factor alpha n. Okay, so therefore when you combine ln and fn, So one will contract in the x direction, another will contract in the y direction. So therefore, this each wn, they will contract any object in both x and y direction. Okay, so therefore each wn is a contraction map. So now therefore, if you take this compact set and this finite number of maps, okay, so their contraction, this is the required iterated function system. So therefore, how to choose the fn xy? Okay, so this question is, here ln you don't have any problem, because if you take ln x equal to anx plus bn, you have two unknowns, two conditions are there, so you can find an and bn. But here the question is how to choose these values. Okay, so this is a map from R2 to R. Okay, so apparently actually, so he told that he proposed this theorem if kwn, so that is the IFS, so this is attractor G such that G is the graph of a continuous function, so that f of xn equal to yn. Okay, so therefore this you find it. So previously we got the IFS, this is in H of R2, so this is a capital W is a contraction map, so therefore you will get a fixed point there. So this fixed point of this IFS is nothing but a compact set, this is a compact set in R2, that means it is element of H of R2. Okay, H of R2 is nothing but set of all compact subsets of R2 which is different from empty set. Okay, so this is the condition here. So this proof actually it goes like this. So let G be the function such that G is continuous, G of x0 equal to y0, G of xn equal to yn. So this is suppose endowed with the uniform metric. Okay, so therefore T is a G to G, it is defined in, this is called Reed-Bajrak-Tabari operator. So suppose this Fn is defined earlier. So you choose your Fn suitably, whatever Fn. Okay, so this may be a linear, or this may be a quadratic, this may be an implicit function, this may be explicit function. So you have to choose some function like this. Okay, so this T of Hx defined whatever once Fn is chosen according to these two conditions. Okay, here this will satisfy this condition and this has to be contractive in the second coordinate. Okay, so therefore T is defined through Fn like this. Okay, so this T is nothing but this is a contraction map, one can prove it, this is a contraction map. So therefore this space is complete, the script G. Okay, and T is a contraction map, so therefore it will have a fixed point. Okay, so that's why if you write here fixed point, so you'll get what is called fractal interpolation function here. Okay, so therefore this function actually, this fixed point, this is called a fractal interpolation function. Okay, so with special choice of map, namely, so if you take ln x equal to anx plus bn, I told you have two unknowns, two conditions are there, you can find an and bn. For fn xy, so this is your alpha n f plus mnx. Okay, so here alpha n, this is lies between -1 to +1. Okay, so for given f actually, if f is given, so we are defining this way, mnx. Okay, so this may be some function of x actually, so we have not put any restriction at this moment. Okay, so it will satisfy this equation. When you will get this fixed point equation, okay, T of f equal to f. Okay, so therefore you will write f of ln x. So this is nothing but fn. So if you write x as ln x, here we will find fn x. Okay, and here when this fixed point h is Tf equal to f, so h will be replaced by f, so we will find f of x. Okay, so this equation, it follows from this expression, because T is a RB operator which is contractive in nature, so it has a fixed point. So you write Tf equal to f. Okay, if you write Tf equal to f, so therefore your f of ln x will be written as Tf of ln x. So if you write Tf of ln x, you'll find this expression whatever is written here. So it will come like this. Okay, in this case you have taken Tn of x fx equal to alpha n f. Okay, so alpha n fx. So this is y actually. In place of y, it is alpha n y. So therefore, if you write f, so this is going to be fx and mnx. So therefore, one can observe actually this f of ln x equal to alpha n fx mnx. Okay, so therefore, this is basically an implicit function. Okay, so it is not like fx equal to x square, you plot this parabola or something like that, or fx equal to sin x, or fx will e to the power x into sin x. So this is not like that. If you see clearly this function f of ln x, okay, this is alpha n fx plus mnx. Okay, so if this alpha n is different from 0, so this is a very implicit function. Okay, so therefore when you plot this function, fractal functions actually, so you have to start with the given data, and from there, suppose you have n number of points are there, next stage you generate n minus 1 into n points, then you repeat the process, you will get all these points. After some iteration, you plot the fractal function. Okay, but if alpha n equal to 0, what will happen here? You will find the explicit expression. Okay, so that whatever is there in the classical spline, okay, if you write f of x equal to mn of ln inverse x, so basically we are defining in different pieces actually. Okay, so therefore in particularly if you see the fractal functions, okay, so they are nothing but they are actually generalization of the splines. Okay, so if alpha n equal to 0, we'll get these classical splines. Okay, so how to generate the fractal function? So this is the idea. So if some points actually, so between these 2 points, so you have total 4 points. So between these 2 points, you have to create 2 more points. Between these 2 points, you have to create 2 more points. So the same thing, you just create these 2 points, then you join them. You'll get a. So this is the one iteration because we don't have the explicit expression. We have the implicit expression. From this given 4 points, you have to generate the function. Okay, therefore, from this given 4 points, we are generating each step here 4, 4, 4. We have 12 points you can see, but some points are matching. Again, from 12 points, you can generate 36 points. Okay, similarly, if you join next stage 32 into 3 or 96. Similarly, if you do after 7 or 8 iterations, this function, these points will be it will be dense actually. Then if you plot it, so you'll find some function like this. Okay, so you can see this fractal function how it looks like. So if you zoom any part of this function, it will be very similar to the original one. Okay, so that is the property of the fractal function. Okay, so therefore this type of nonlinear function, they are easily capture whatever nonlinearity associated with any type of a natural phenomena. So you can change it according to your stock market data or ECG data or EEG data, whatever may be the. Okay, so that's why these functions are very popular nowadays in pattern recognition, okay, signal processing, image processing. So okay, so this existence of spline FIF was introduced by Bransley. So Bransley, what he proposed actually, one can construct a smooth function whose derivative will be like this. Okay, so therefore, so he told actually how to construct such a function. Okay, but his splines were not flexible. Okay, if the derivative values are given at the initial endpoint, so sometimes when you construct the splines actually, we give the boundary conditions here both ends, not only in one end actually. Okay, the Bansley construction, it says that if you know the function values or derivative values in the left endpoint only, then you can construct the spline fractal interpolation function. It was very complicated, so therefore this construction has been generalized. We have given a very simpler method how to construct the cubic spline by using the fractal methodology. Okay, it was long before we did this work. So like if you have a cubic spline, what is the nature here? You see the fractal cubic spline. Okay, so this is the data x0 to y0. It has to pass through all these points. Okay, so this has to be C2. Okay, I am not taking C1. C1 is very easier. So C2 is cubic spline because if you take cubic one, because when you take the linear one, affine one, it is continuous. So therefore, if you integrate it is quadratic. If you integrate twice, it is cubic. So that's why it is very natural that whether we should get a twice differentiable function which is satisfying the interpolation condition, and this should be fixed point of the some iterator function system. Okay, because it is coming from the fractal methodology. So therefore, we need a fixed point here. Okay, so here you can observe this is a cubic spline. So therefore, if you take the double derivative, okay, but this is a fractal function, is implicit one, but this part is a cubic spline. This part a cubic function. So if you take second derivative, it is a linear one, but I have in a particular fashion Cn x minus x0, xn minus x0 plus Cn. So therefore, if you integrate this function 2 times, okay, then you have to add 2 arbitrary constants. Okay, by using the interpolation condition f of x delta xn equal to yn. Okay, so if you put this condition, then you can evaluate that constant, the 2 integration constants, and then if you put that one, you'll get this expression. This is okay. So this is your fractal cubic spline, but here you need all these values of mn. How to get these values of mn? Okay, so therefore, what we'll do here, we can put the fast derivative or continuous. This method is very similar. Whatever do in the classical cubic spline. Okay, you would write a here alpha n will not be there. Here you have an this part will not be there. Okay, you put a double derivative, so it is a linear polynomial. Then you start from there. Okay, you'll get similar expression in the classical cubic spline, which is twice differentiable. You are generalize that construction to the fractal one. So therefore, this is the okay. So general cubic splines. So here if you write L equal to xn total length equal to xn minus x0 from the continuity condition f dash xn plus 1 equal to f dash xn minus 1. So here you can see this is defined over different pieces. Okay, so therefore when there is a knot actually, so you are defining two pieces. So we are imposing that the tangent has to be continuous. So therefore in that case, okay, so if you go from left or right actually in the joint, you have to check whether they are satisfying that condition or not. So we put that condition here. Okay, so therefore you have n minus 1 joints are there. So therefore you will get here n minus 1 condition. Okay, because n plus 1 data points are there, you have n minus 1 joints are there, you will get this condition. Okay, so similarly, but here you have the problem. Here this will contain actually, so all these y0 to m0 to mn, these are the unknowns. Okay, but here you see the number of unknowns is n plus 1, but unfortunately you have n minus 1 equation, you cannot evaluate them, okay, as per your convenience. Okay, so therefore you have to choose two more conditions. The same deficiency is there in the cubic spline. Okay, so when you construct the cubic spline, generally you have to choose the two conditions. Okay, like if you take the derivative values, you get the Coulomb boundary condition. If the double derivative is given, actually you get the boundary conditions of type 2. If the double derivative are 0 at the endpoints, you get the natural cubic splines. Okay, so therefore you have different type of splines are there, or periodic splines are there. So you have to put on other conditions there. Okay, so therefore if you differentiate 2 with n equal to 1, so here we don't know what are the values of mn's. Okay, but you take the derivative of this value at n equal to 1, so you'll find d0 is there. So d0, the derivative value to satisfy some condition. Okay, similarly if you take n equal to n at the last end actually, so this derivative dn will satisfy another condition. Okay, so therefore in the factors line you are finding two more additional conditions which are coming from the derivative values. Okay, so what happens now, you have these two more conditions are there. So earlier you have n minus 1 conditions are there, n minus 1 plus 2, those are now you have n plus 1 conditions are there. Okay, so but you have n plus 1 unknowns because m0 to mn plus derivative values. So therefore you have to choose two more conditions arbitrarily. Okay, so if you choose derivative, first derivative or second derivative or anything you choose as per your choice, so that these equations with n minus 1 equation, they are going to be linearly independent obviously. So 3, 4, 5. So if you take 3, 4, 5, but one can write the system of equation here. Okay, but the deficiency is 2. Still you can choose more conditions so that you can fill that deficiency and you can get all these values of d0, d1, d0, dn and m0, m1 up to mn, then you will get your spline. So this is the, so once you get these values, you can put it here and then you will get your fractal cubic spline in this way. Okay, so now this question is whether I can use this fractal cubic spline for the solution of the differential equation. Okay, so first case, actually I have taken a differential equation, a linear differential equation with constant coefficient with very simplistic Dirichlet condition, Dirichlet boundary condition. Okay, second one I have taken a little bit complicated. You can take the nonlinear differential equation with Dirichlet boundary condition and can change the boundary condition. It is not a problem. So here what is the type 1 cubic spline? You give the derivative values at the first endpoint. So that is basically they are called clamped fractal cubic spline. So these points, the derivative values are fixed. Okay, so therefore this is the cubic spline. So here if you see the second derivative, you can see this is the fractal function. So it will not there in the classical spline actually. In the classical spline, if you take any sorts of spline, if you take the second derivative, here you will find this is a continuous, this is a piecewise function or this is a very smooth function. Okay, but in the this type of fractals case actually you can see these functions are very complicated in the nature. Similarly, if you change the values of alphas, then you take the derivative, you see again you are getting very wild functions. Okay, so therefore if you choose these values of alpha, these are very complicated. It means different values, so one can find very complicated functions here. But you observe these values are close to 0, you will get the linear, this classical cubic spline. Okay, so here also I have given type 2. Okay, so sorry, type 1 you have d0, it is given actually. So the second derivative I want to show actually. So if you take alpha equal to 0.50, so one can see this is this piecewise spline actually. So between these one, so this is going to be a piecewise spline. Okay, sorry, 3 to 4, 3 to 5 actually. So this part. So here alpha is 0 actually. So you can see this part alpha is 0. So therefore there will be a straight line basically. Here they are straight line. If alpha is non-zero, you'll find this type of very complicated structures are there. So in previous case, you see all these alpha is are non-zero. So therefore, you are getting the notorious function. Actual functions looks like smooth, but derivative is very irregular. The same thing is happening here, but it is because these values are small, so therefore they are not that much wild actually. Okay, so therefore if you take everything equal to 0, alpha equal to 0, everything is 0, so you'll get actually the classical cubic spline. Here the first derivative is piecewise smooth, you can see it. Okay, so therefore whatever we are getting here, fractal splines, they are basically generalize the existing spline. So now we'll come to the second order boundary value problem. So this is your y double dash equal to f of x, y dash. Okay, so this is your y dash a hat equal b1 star, beta 1 star, y b hat equal to beta 2 star. So this is your second order boundary value problem with the boundary conditions. Scalar actually, he proved the existence of this unique solution of this differential equation under certain conditions. If you assume this right hand side is continuous on a domain, okay, and then dou f by dou y dash, they are also existed, they are continuous on this domain, okay, and dou f by dou y is non-negative and less than equal, modulus is less than equal to k for some k belongs to 1. If these conditions are met actually, then one can say that the second order boundary value problem, okay, so that will have the unique solution. Okay, so if you want to see that one, it is given this as BKL or numerical methods for 2-point boundary value problems. Okay. So we know actually if this is the second order differential equation with real boundary conditions, okay, so we can get its solution. Okay, the question is whether if something is there, this function can be modified actually. So if the differential equation is modified to a linear differential equation with a complicated fractal function. Suppose you take the linear 2-point second order boundary value problem, we like this y double dash x plus qx y dash x plus pxy equal to rx. Okay, so now you are taking a linear second order non-homogeneous differential equation. Okay, so this is the Dirichlet boundary conditions are given. Okay, where rx, so the right hand side, it may be nowhere differentiable. Okay, so if you take nowhere differential function the right hand side, then the derivative of this function is restricted. Okay, so if you take actually more differentiability, then it will not match with the right hand side, because if it is infinitely differentiable, okay, so this function is infinitely differentiable. Qx is something very smooth function that is also multiplied here. This is infinitely differentiable. This is infinitely differentiable. Okay, so therefore what we are getting here, the left hand side is infinitely differentiable, but right hand side is nowhere differentiable. Okay, so therefore this will not match actually. Okay, so therefore those classical solutions, they will fail actually when the right hand side is a function which is nowhere differentiable function. Or if you see this px is also a continuous function which is nowhere differentiable, then obviously the classical solution will not work. Okay, and you have the Dirichlet boundary conditions are there. Okay, so here how to get the solution. So what you do here, you discretize the boundary. Okay, so first point is x0, last point is b, you take as xn, not necessary to have uniform partition. Okay, so when I am taking the linear one, so I don't use the uniform partition. For non-linear case, for simplicity, one can use the linear one. The uniform partition. Okay, we should require a spline FIF which satisfy the condition. Okay, so you discretize. Okay, then you'll get the system of equation here. Okay. So it is clear that using 3, we obtain the set of relationship from the unknowns actually. So this, we are going to solve this differential equation subject to this boundary condition. Okay, so our claim is because the fractal splines actually, so they are twice differentiable and double derivative is a continuous function which is nowhere differentiable. Already I have shown you. Okay, the double derivatives are very irregular. So therefore, if I take my solution like this will work. Okay, so therefore the right hand side is a nowhere differentiable function. Then I think to choose appropriately your yx, then if you take double derivative, add with multiplication of y dash x, px, yx, that will work. Okay, so this is the basic idea. The question is you just discretize the domain. Okay, so these are the nodes actually, xn, n belongs to 0 to n. Okay, so now we have the set of relationship between the moments m0 to mn. Okay, so now we obtain the result, and with the boundary conditions 8, we can determine the values of y0 to yn. Okay, using all these values into, we obtain the desired fractal solution. It is clear. So what we'll do actually, so we'll find what are the m0 to mn. Okay, then we put everything in the given expression. Then we'll get actually the fractal spline solution for the given differential equation. Okay, so now I'll take different cases. So here suppose qx equal to 0. So coefficient of y dash equal to 0. Then we find y double dash plus px yx equal to 0. That is basically the normal form. Okay, so if this is like this, okay, so if you take x equal to any value xn, actually here you will find mn as per our notation. Okay, right hand side is rn. So this is pn, this is your yn. N equal to 0 to n. Okay, so immediately if you discretize it, put x equal to xn, you will get the values in terms of moment double derivative at xn. All these values are known to us. Okay, so this is the discretized values. Okay, so now you got these values mn, whatever may be the r of rn. Okay, so you discretize the given equation. So you take these values 10 and put in the given differential equation 3. Okay, so in the differential equation, so this is your actual mn values are given. So we can put those values there. Okay, so this equation will be reduced like this. Basically, you have to compute the values of yn. Okay, from these equations, you will get the values of mn. Okay, so mn values are known to us, n equal to 0 to n. So from 10, so you put the values of mn like this, so then you will get the system of equation. Then you compare the coefficients. Okay. So here you have n minus 1 number of equations will be there. Okay, from 4 and 10, again you will find one more equation at the left end point. Okay, another equation in the right end point. Okay. So these two equations are ready. Okay, so if since y0 x0, so these values are given because we are using the deleted boundary conditions. Okay, so therefore these two values are given. So we have need to compute n plus 1 unknowns from n plus 1. N plus 1 unknowns from these values y1 to yn minus 1 d0 to dn. You can see now they are matching actually. Okay, you have n plus 1 unknowns are there, so you'll find n plus 1 equations will be there. Okay. Because here you have n minus 1 equations and you are taking two more conditions, so therefore you have n plus 1 equations. So if you solve it, you'll find all these values of m0 and d0 dn. Okay, you put everything in the given differential equation 2. Okay, you'll get the fractal spline solution. So therefore you can see this expression. You need mn values and derivative values, so you put derivative values, you'll get it. Okay, because from d0 dn you can find the values of y0 yn, all these values are there. Okay, so we'll get the fractal solution in this method. Okay, the second one is suppose qx not equal to this px not equal to 0 and qx not equal to 0. So here px not equal to 0, earlier px equal to 0. So now you assume qx not equal to 0. Okay, and px also this is not 0. So with deleted boundary condition like this, okay, at x equal to xn, you can discretize this function pn, dn, qn, yn. You can see when x equal to xn, you'll find y double dash xn. Okay, p of xn, here y dash of xn is dn, qn of yn equal to rn. So now you have n plus 1 equations are there. Okay. Yeah, so therefore at xn you will find these n plus 1 equations are there. Okay, so now you put the continuity f dash xn plus, it will be like this. Similarly, one can see what is your f dash xn minus. Then you equate them, what will happen at the joints actually. Okay, so f dash xn plus 1, f dash xn minus 1, you have to put the derivative conditions are continuous. So therefore you will get actually, so this is the condition for f dash xn. So now you have to match. Okay, because first derivative is continuous, these are C2 interpolant. So therefore you can equate 17 and 18. So therefore you will get a system of equation like this. Okay, similar system of equations is available. Okay, in the classical case, if you take alpha n equal to 0. So it will match with the classical case if you take all alpha n equal to 0. So therefore elimination of mn from 19 using the explicit formula in terms of yn minus 1, yn plus 1 give the following relation. Okay, so therefore if you derive these values from here, okay, by using this formula, so you'll get a system of equation like this. Then you solve it, you'll find all these values of yn. You'll find a tridiagonal system, then you have to solve it. Okay, it is in particular, you'll find all these values of lambda 1n, lambda 2n, lambda 3n. Okay, so therefore if you take two more additional conditions, then you can evaluate all these values of yj. Okay, so finally the cubic spline fractal solution of this bounded value problem is obtained. So therefore, two cases, whether you are taking px equal to 0 or qx equal to px not equal to 0 or qx not equal to 0. Okay, so when the scaling factors are taken to 0, the partition points are equally spaced. Okay, then the spline F5 reduces to the classical spline function as discussed on this literature. It was done in 1969, I think. Okay. So when you select the partition points are equally spaced and equal scaling function, then this equation 11 actually, so whatever things you are seeing here, little bit complicated there, this equation. Okay, but if you take it equal spacing actually, okay, so it reduces to very simple condition. Okay, when they are equispaced, you'll find this is equal to a square. Okay, so this a is cancelled out. Okay, a is basically this an equal to a. Okay, so distance between xn minus 1 and xn divided by xn minus x0. Okay, so that if that value is fixed actually, when you take uniform partition, those values are going to be same. So I put that value here and you'll get this expression like this. So this is basically, one can see this is correspond to central finite difference approximation of this derivative. Okay, so what is the truncation error? If you want to compute the truncation error, then one can see what is the truncation error associated with this. Okay. Then one can compare the analytic solution and the fractal solution, how much the error are varying. All these results are there. So we'll see one example. So now you consider the 2-point boundary value problem. So y double dash plus pxy dash plus qxy equal to rx. Okay, y of 0 equal to 1, y1 of equal to 2. So now this question is, suppose rx is a continuous function which is an overhead differential. Okay, then how to find the solution? Suppose here px equal to x square plus 0.1, qx equal to sin x plus 0.1. So I can get this expression. Okay, so these are the implicit expression. Okay, but if you take this one, okay, so no classical method will work how to get the solution of this differential equation. Okay, so what we'll do here, so Rx is, suppose here is a continuous function, you know where differential function. Okay, it is very regular function is there. So in this case, as we discussed actually here, the solution should be a fractal function, means twice differentiable, but the double derivative is a nowhere differential function. That's why it has to match actually. Double derivative, here you are finding Rx is nowhere differential function. So what we do here, so this is the differential equation, y of 0 equal to 1, y1 of, so we want to get the solution of this differential equation. So you do the partition of this interval, like x0 equal to 0, x1 equal to 0.4, x2 equal to 0.75, x3 equal to 1. Okay, suppose Rx, from the graph of the Rx, suppose you'll find R0 values like this, R1 value equal to this, R2 value this, R3 value at these points. Okay. So in that case, so here you just see Rx value, since I have the plot actually of this function, I can get these values at any point. Okay, because this is the fractal function I have generated. Okay, so now I am putting that one in the differential equation, then I have to find the solution. That means I need a spline, fractal spline actually, whose second derivative should be a continuous function but no differential. Okay, so therefore this has to be done carefully. Okay, so you do the discretization of this. Okay, so what is the value of R0, R1, R2 and R3 are the grid points? You can get it immediately. You take the alpha n value equal to 0.8. Okay, thus from 4, 5 and 17, 20 we obtain the system of equation with unknowns y1, y2, d0, d3. Okay, because you have the two more unknowns are coming, d0 and d3, because they are the slow values. Okay, so therefore naturally we need two more equations. So therefore, after if you solve the system of equations, whatever I said actually, if you set two conditions are there, okay, so you can get the values. Suppose these values of d0, d3 is given, that means cubic splines of type 1. In this case, you'll find m0 equal to this, m1 equal to this, m2 equal to this, m3 equal to this. Okay. So by using these values, one can get the value of y1 equal to 1, y2 as minus 1. So therefore this approximated fractal solution, so this can be written as in this implicit function will be like this. Okay, fx equal to 116 by 125 f of x minus 1669 by 2500 x cube plus 4 by 125 x square plus 129 by 50 x. Okay, so if x belongs to these values. Similarly, if you take the other interval, this is the expression here. Similarly, if you take the last interval, this is the value. So these are the implicit function. You can see when you put these constants as 0, you will get the explicit expression, you will get the classical cubic spline. Okay, so this is the original solution. So if you take the cubic fractal spline solution F1, so this is very close to the original solution. If you take cubic spline fractal 2 actually, so that is also very good solution. Okay, similarly, I have taken another classical cubic fractal solution. This is also good, this is also good. Okay. So, but what is the error actually? Okay, so these are the different solutions. So what we'll do here, you plot the original function and all these approximate solutions. So you can see this is the data points. Okay, so these are the data points. This is the general solution. This is the F1. So similarly here you can see this is the general solution, blue one, and this is the approximate solution. So I have given several examples. Okay, and one of this example here we have the classical solution. Okay, so this P is the classical solution. One can find actually F1, F2, F3, F4. This is the P classical spline solution. Okay, if you compare the error associated with this these splines with the original function, then you'll find with the polynomial function it is very much clear. Okay, if you take the classical spline actually, so that has the very error is too much. Otherwise, in the fractal spline, the error is very small. Okay, so these computations are given actually if you give values of alpha like this D0. All these cases actually whatever we tried with various experiment. Okay, we change the values of derivative, then you see which solutions are working better. Okay, so that's why this theory can be improved actually, how to choose the values of DI, how to choose the position of the knot points. All these are the open problems now. Okay, so these are the scaling factors. These are the derivative values. Okay, so therefore you'll get your M0 values. Then you can write the spline. Similarly, here this is the value of alpha. These are D0, D3. Then you will find the M0, M1, M2, M3. Similarly, here these values of DIs are given. Okay, and values of alphas are given. So you have to compute the other values M0, M1, M2, M3. Then you put everything in the given spline function, and you'll get the different type of splines or different pieces of the spline. Okay, so one can compare the error. So if you see the error between the classical one, it is very large. Okay, fractal one also it is large, but one of the fractal has very small solution. S minus F1 equal to 0.140. Okay, so therefore the chances if you choose appropriate values of your root. Okay, so what are the roots actually, and what are the scaling, then you will get this error is going to be very much minimal. Okay, so note that the solution of boundary value problem is not unique. If Yx is not, as Yx is not infinitely differentiable. Okay, so when you assume y double dash is not differentiable, okay, then it is possible to get a wide variety of solutions by fractal methodology. Okay, so why you need the fractal methodology? You can understand actually we need the, so even if these are the fractal solutions for the differential equation, but if you seek the second derivative, these are very wild functions. Okay, so they are like this. So I have shown actually, so these are wild functions are like this. So therefore one can get the smooth function which derivative are very wild actually. So that's why we did it. Okay, so similarly, we can consider another differential equation, y double dash plus y plus 1 equal to 0, y0, y1 equal to, this is analytical solution of this function is cosine x tan half sine x minus 1. Okay, so how to get the fractal spline? This is a differential equation with constant coefficient with the little boundary condition. We can apply our method. Okay, so you take this, divide into two parts, x0, x1, x2. Okay, so here you'll find h1, h2, h equal to half, because obviously the whole interval is coming to the half. So L equal to 1. So A equal to 1 by 2. Okay, so therefore alpha equal to, it has to be smaller than A. So in practice, it has to be smaller than A. So therefore I have taken this as 0.1, alpha equal to 0, 1, 2. Okay. So now f dash 0 equal to d0, f dash 1 equal to d2. So you give these two values. Okay. Then you can, they are calculated from the end point of this equation. Okay, so from the end point of the equation, we can get the values of d0 and d2. So now we have these conditions are there. From this, you'll get the values of m2 and m1. You put everything in the given differential equation. Given equations like f dash 0 now can be computed like this in terms of d0. Okay, this value is given to us, we can find the d0 here. Similarly, if this value is given, you can find the value of d2. The d0, d1 is ready. Okay, then you put these values here, you find all these values of moments. Once moments are ready, then we can get the fractal spline solution. Okay, so this is the fractal spline solution. Here we have the fractal spline solution. Okay, so if mi's are known to us, then we'll get the fractal spline. Okay. So here we have given some example. Okay, so where you can see that this is the general solution. So this dot one is the fractal solution. You can see it is very close. Okay, so this is the analytic solution, but fractal solution here deviating. Okay, but here you can see this is the original solution. And this is a classical solution. It is also very high error here in this case. Okay, so how to do the interpolation point? Then you need some additional tool actually from wavelets. Okay, then how to optimize the values of alpha I? That means you have to do some simulation and optimize the values of alpha I. Okay, for approximating the boundary value problem by using the fractal spline method. So now this is also another type of fractal cubic spline solution. So this is quartic fractal solution of the fractal spline solution of the boundary value problem. Suppose you take the data points A hat, B hat, just to make the notation a little bit different, I put this in this manner, but otherwise if you want, you can put x0 to xn. Okay, here this is, you take a grid points, this has to be uniform, because here we are allowing actually Runge-Kutta method, so that's if it is equal partition, it will be easier for us to compute all these values. Okay, here we will use the sorting method and Runge-Kutta method, so that's why we assume that partition should be uniform, otherwise it is very much complicated to handle this problem. Okay, so let modulus of I equal to distance of this interval xn minus x1. Okay, suppose the solution of this boundary value problem is given by 6, which is at least 3 times differentiable. Suppose you assume the solution is known to us. So here yi equal to y of xi, mi equal to y double dash xi, zi equal to y triple derivative at xi. Okay, so therefore in this case, so these are unknowns. Okay, so these values, suppose this value we need this function to be thrice differentiable, because here I am going for the higher order smoothness. I want the solution has to be 3 times differentiable. Okay, I am assuming this mi, zi are given, or this has to be computed in some ways. Okay, so consider the contractive homeomorphism as we did earlier. So you can write ex plus ba, because here it is the fixed. You have the equispaced actually grid point, so E equal to fixed here. Okay, earlier it is ai, it is varying because the grids are not equispaced. Here grids are equispaced, therefore these values of E is fixed, s by modulus of I. Okay, and bi you can compute like that. For the IFS we need n minus 1 number of continuous maps, so that it will satisfy this condition. This is called join up condition. This is, I already explained this one earlier. This is should be contrasted in the second coordinate. Okay, so this is your IFS. LIX is the first, it will take the care of the contrast in the x, take care of in the y direction. So this is the IFS here. To generate the C3 interpolant, so basically we have to use the principle of the construction of differentiable fractal function. Here the scaling factor alpha I has to be less than e to the power 3, because this function has to be 3 times differentiable. If it is n times differentiable, alpha I should be less than e to the power n. Okay, it depends on the number of times the function is differentiable. Okay, here you need to construct a quartic polynomial, so therefore you have to put a 4-degree polynomial, and here it is again you can see alpha I, this is implicit function, because left hand side it is f of lix. Okay, so it defines for alpha ifx plus qix, again it is implicit function, but here subject to condition, these conditions are there actually. Okay, so these are the interpolating conditions, these are the continuity conditions, where these are the condition coming from the branch layer construction, you put this condition. Okay, so now you have to evaluate all these coefficient of this quartic polynomial. We don't know what is Vi, Xi, Ai, Bi, Ci, because these are required to find the solution of your boundary value problem. So you take this space like this, G C3 3 times differentiable G of x1 equal to yn, G of xn equal to yn. The derivative also match at the endpoints for p equal to 1, 2, 3. So this is a complete metric space with the metric induced from C3 NUR. Okay, so one can check this is a complete metric space. Okay, so therefore we can define RB operator like this. Okay, so one can prove that all these maps are contraction. T alpha is a contraction, so it is a, the space is a complete metric space, so it has a fixed point T alpha f, so zeta equal to zeta of x, so therefore T alpha zeta Lix equal to zeta of, this is a fixed point equation, this will be like this. Okay, from here you will find alpha I, so G is your zeta of Lix, so therefore you will find the same x, zeta of x plus Qix. Okay, so therefore you will get your expression like this is the implicit expression. You have some conditions are there, interpolation condition and derivative conditions are there, double derivative conditions. You put everything from the given differential equation. You try to evaluate Vi, Xi, Ai, Bi, Ci. Okay, so you have to evaluate these values. So if you put those conditions, you will find Vi, Xi, Ai, Bi, and Ci. Okay, so these values can be obtained by putting the interpolation conditions and the continuity condition. Okay, so once it is ready, so you put everything in the given differential equation. So you can check the differential equation. The solution has to be continuous, and double derivative has to be continuous. First derivative has to be continuous. You put this equation. You write the spline in different subintervals. Then you equate them actually for the continuity condition, and you will find a system of equation for this. Continuity of the first order derivative, similarly continuity condition for the second order derivative. So you'll get two equations. From here you have to solve the values of mi and zi. See, if these values of mi and zi is known to us, then you can get these values actually. Okay, so these values are known if you know this expression actually. Okay, this vi, xi, ai, bi, hi, so these are computed in terms of this zi and mi's. Okay, so you know alpha I, how to take alpha I. E is known to us, h is known to us. Only the things which are not unknown to us is mi and zi. Okay, so if you solve the system of equation and find the mi and zi, then you are basically getting your cubic spline. Okay, so now you have to put these join up condition for the derivative values and second derivative values. You will get two equations, one for mi, one for zi. Here you can eliminate these values of mi. So you will get the equations mi like this. So therefore, from the previous equation, if mi is like this, you can write what is mi plus 1, what is mi minus 1. You put this expression in the given differential equation, then it will reduce to like this. All these mi's will be computed and you will find a relation between yi's and zi's. Okay, so if yi's are known to us, then you can compute the values of zi's. Okay, and this equation will be there from 28. Okay, so now from 27 and 28, one can eliminate mi and you'll get these expressions will be like this. Once mi is known to us, one can write mi plus 1 and other moment values like the similar expressions will be there. You put in the given differential equation. So therefore, you'll find a system of equation like this. Okay, so now this problem is what is the value of m1, mn or some values actually. So if some values are given, then easily you can compute all these values of zi's. Okay, so now if you differentiate this equation and put I equal to 1, x equal to x1, you will get one condition for the derivative. Similarly, the last point, okay, you take the derivative, put x equal to xn, you will get another condition. Okay, so now you have n minus 1 condition, you have two more equations are there. You have n plus 1 unknowns are there. Okay, but your derivative values are also unknown. Okay, so you can see all these computations are like that. Okay, so we need to compute the values of mn and zn so that you'll get our quartic cubic spline. So here all these procedures are given actually. See, if the values of all yi's are known to us, then we have to compute the values of only 2n, mi and zi. Okay, so this yi can be computed by using the finite these values of by Rangekuta method or shooting method actually. So one can use it to get the values of yi. So once these values of yi are known to us, then you can compute the values of mi, zi. Okay, don't compute the values of mi, zi first, then yi. This has to be done reversely. First, you have to compute the values of yi by using some numerical method, like Gange-Gupta method. Okay, then you can compute the values of mi and zi from the system of equation. So that has been explained here. Okay, how to get the system of equation and how to solve it. Okay, here you'll find if you're choosing the value of m1. Okay, so other values can be written in terms of this yi and zi. So therefore, basically, you have to choose three conditions apart from m1. So if to z1, zn, m1 equal to 0, you'll find the zeta x1, zeta dash xn, and mn. So you put all these values, okay, and then you'll get this system of equation, and then you can solve these values to get the yi's. Okay, so this is the for convergence condition. You need the alpha has to be chosen e to the power 3. That means alpha has to be less than sq actually in this case. Okay, so if you choose actually z1, zn, m1 equal to 0, you'll get one more condition, or if you choose different values, you'll get similar condition here. Okay, so this procedure goes like this. You choose the partition of this interval. Okay, so find the function values of yi by using some shooting method to the boundary value problem with fourth order explicit Gange-Gupta method, because you'll get the yi which be, all these yi, they are going to be very close to the original solution in this procedure at step 2. Okay, so now using these values of yi's, okay, so you take m1, z1, zn equal to 0. Okay, then you can compute all these values of zeta dash x1, zeta dash xn, mn, and zn. So now all values are known to us. So you put all these values actually, and then you find the values of all mi's. Okay, once mi's are ready, then you can put these values in the second derivative of mi and third derivative values of zi in the equation 25 to get the neat the desired numerical solution of this fractal boundary value problem. So that has been explained. So here the convergence, due to time constraint, I think I'll move quickly. So I will not tell actually how we have done it. Suppose you assume the y belongs to, because in classical case they have assumed this function has to be fifth time differentiable, because we are using the Gange-Gupta fourth order Gange-Gupta method. So therefore we need some assumption to be little bit stronger here. So this is the solution, fractal solution here. Okay. So you see what is your approximate solution, what is your original solution. Okay, so then we try to get the error between these two values. Okay, and here the computations are given how to compute this error actually. So one can observe that the uniform error between the original solution and the fractal spline solution is going to order to the power HQ. Okay, so here I have given some example. Okay, here it is not necessary to take a linear equation. One can take non-linear equation to solve it. Y double dash equal to 2yqx. Okay, y of 0 equal to 1 by 3, y of 3 equal to 1 by 6. Okay, here x lies between 0 to 3. Okay, so here you see the proposed solution. So our method is giving your blue method. So this dotted line is the classical quartic solution. Okay, this orange line is the original solution. Okay, so one can see actually, so our solution is close to the original solution. Okay, similarly, if you see over the, if you zoom the what is the happening over the 0, 1, one can see actually the fractal solution, which is the blue color. It is very close to the analytical solution, yellow color. Okay, but the classical solution is deviating too much. Okay, so therefore fractal solution will give the least error. So here you can compare the fractal solution. This error is 0.0038, where the classical spline solution is 0.47. Okay, so therefore naturally this fractal spline solution is better than the existing solution. Similarly, consider another differential equation, y double dash x equal to yx plus fcx. So it is a continuous function which is a differentiable function. This is plotted here. So similarly, you can adopt the previous procedure. You need a quartic spline solution. Okay, so here you can see what is the original solution. The original solution here, it is the yellow one. If you take the classical spline solution, the dotted one, which is error is too much. If you are using the fractal solution, it is very close to the original solution. Okay, similarly, we have given another example here. Okay, so this is the second order differential equation satisfying this condition. Again, you can use the fractal quartic spline solution. Okay, and classical quartic solution. One can see this is the classical spline solution. It is deviating too much. Okay, but the fractal spline solution is very close to the original solution. Okay, so therefore one can solve different type of the boundary value problem. Okay, by using the fractal spline. So this is the starting point. Okay, so it is hardly anybody has done substantially in this area. So this is the upcoming area. So if you choose different type of fractal spline, so one can solve the different type of boundary value problems. Okay, similarly one can solve actually the integral equations by using the fractal interpolation function. Okay, suppose this phi x is a nowhere differentiable function. Okay, so therefore here the smooth function, this is a nowhere differentiable function. So therefore one can actually expect that ux is going to be a nowhere differentiable function. Okay, so because the classical solution will not give the exact solution in this case. So therefore if you choose a fractal solution, this is going to be a very good solution for such type of Volterra integral equation. Okay, so what we do actually discretize the domain. Okay, and then we have to discretize over this integral actually. So one can go for the trapezoidal method here. Then you find the values actually, you see what is your unknowns, how many unknowns are there, how many equations are there. Based on the discretization, one can get the solution here. Okay, so here I think if you take the ux is like this, the Volterra integral equation. So this is your Volterra integral equation. This is a stress function. So this is like this. So here actually we know what is the exact solution here. So we took some interpolation data, then we use the fractal methodology, and then this is the solution actually. So we found the fractal spline solution for the integral equation, for the Volterra integral equation. Similarly, one can develop this result for the rational spline. Okay, and one can go for the differentiable. Suppose this is the differentiable function, but derivative is a continuous function of a differential function. There you need the rational spline. So how to do it? Actually, we developed the procedure recently. Okay, till one can get the solution here by using the fractal rational splines. Okay, similarly one can develop the fractal Galerkin method. Okay, so this is not developed fully actually. So just some outlines are there. So I will not cover it in details at this point. So we leave it. Okay, so basically I cover how to find the fractal spline solution for the boundary value problem, or how to find the solution of the elementary Volterra integral equation by using the simple affine fractal functions. Okay, and we prove some convergence results. Okay, so this is the new area, upcoming area, which can be used to solve some differential equation which is arising in the different type of nonlinear problems. Okay, if the differential equation as a continuous function which is nowhere differential function, then it is better to apply the fractal methodology in the solution of the differential equation. Okay, so these are the few references. Okay, so that is used for the solution of develop this theory. Okay, so I use some result from this paper, this reference, and some result from here as well. P and this is 13. And these are the traditional methods. So these are the some new results actually, how to use the fractal quintic spline method for solution of nonlinear boundary value problem. This is the how to use the fractal spline for the singular boundary value problems. Okay, so these are given recently. Okay. Thank you for your kind attention.
Thank you so much, sir, for your enriching words today. We are immensely grateful to have you here with us today. Thank you for joining us today, sir.
Okay, thank you. So do you have any questions or do you have any doubts?
If anyone has any queries or doubts, you feel free to ask, sir, regarding those.
Okay, so it may be difficult to answer.
Yeah, which kind of boundary conditions you consider?
Here I have used simply for simplicity. I have used the Dirichlet boundary condition. If you use Newman or Robbins boundary condition, then accordingly you have to check actually what is happening to the other two conditions, because when you construct the fractal spline, there is a deficiency is there. Okay, so in boundary condition, basically you will get two conditions. Okay, still apart from those two conditions, you need additional conditions, so you can change the boundary condition. Okay, for simplicity, we have gone for this Dirichlet boundary conditions. You can go for Newman or Robbins boundary condition.
Okay. Thank you, sir.
Thank you so much, sir, for
Okay,
joining us
thank
today,
you.
sir. So, with this, we have come to an end of our 4-day program today, and we hope everybody has learned and enjoyed today. We thank everybody for their cooperation and patience today. So, thank you, everybody, for joining us.
Okay, thank you.